Hey everyone, this is Dr. Walker. In this video, I'd like to go over the second example from v583 on Faraday's law. In this example, we're inducing an EMF in a coil. We have a coil that consists of 200 turns of wire. We can imagine a coil. Let's say that it's lying flat here in a plane perpendicular to the page. And then it's actually a square coil, so that is actually a lot easier to draw. All right, a square coil. Let's say it's perpendicular to the plane of this screen here. We're given the dimensions, and then we have a uniform magnetic field directed perpendicular to the plane of the coil. So let's say we have a field going straight up, perpendicular to the plane of the coil. From 0 to 0.8 seconds, the field changes linearly from 0 to 0.5 teslas. So we know that the field through this loop is changing, which means that the flux through the loop is changing. And Faraday's law says that when this happens, we're going to have an EMF induced in the coil. We're trying to find the magnitude of this induced EMF. So we know that Faraday's law says the EMF is negative N and then derivative of the magnetic flux with respect to time. And if we're just looking for the magnitude, then we just don't worry about the negative sign. So we need to know how the flux is changing. In this case, for part A, the field is changing linearly per time. The area of the coil is not changing. So we can rewrite this as the flux is AB cosine theta, right? But the area vector is perpendicular to the loop as well. So we can see that when the field is perpendicular to the loop, that A and B are parallel, and the cosine, let me just write this on the side here, BA cosine theta, we know that the cosine vanishes when the field is perpendicular to the loop. So we can write this as the change in AB over time, and the area is not changing, so we can take the area out. So we can write it as NA change in B over change in time. And we can go ahead and plug in our values. The number of turns is the 200 here. The area, well, we have a square, so we know the area is going to be length times width, or d squared. So that's going to be 0.18 meters squared. Can plug that in. And then change in B per time. Well, we're told that from 0 to 0.8 seconds, it goes from 0 to 0.5 teslas. So the change in field is 0.5 teslas, and that takes the change in time here is 0.8 seconds. So no calculus necessary for this part. We're going to get 4 volts when we solve this part. Now let's look at the second part, which says that after 0.8 seconds, then the field decays in time according to the expression B is equal to B max e to negative AT, where A is some constant, and we have our B max of 0.5 teslas. So we're looking for the magnitude of the induced EMF in the coil. We can write down Faraday's law, just the magnitude of it. We don't worry about the negative sign. And this time, we need to go ahead and write out. Once again, the field is still perpendicular to the plane of the loop, so there's no cosine term that we have to worry about. But we're going to take the derivative of AB, where B is going to be B max e to negative AT. So we're going to take the derivative of this whole expression with respect to time. So we can take out the constants here, A, B max, and we're going to have D of e to the negative AT over dt. All right. And now we can go ahead and solve this. We know that we're going to have NAB max, and then we're going to have negative a and e to negative at. And now we can go ahead and plug the values in, and since we are taking the magnitude, we still don't care about the negative. Go ahead and plug in all of our values, n. Well, we can bring the a in front since we don't have a value for that. But n is 200, then the area is still the 0.18 squared. B max is 0.5 teslas. And then we have e to negative at. So we do see that the EMF induced is a function of time, and then we just need, if we are given a certain time, then we can just plug it in, but otherwise this is our final answer.